Hello. This video is going to be about lead lag control, controlling a simple motor system. So to start with, I'm going to show what a lead lag filter looks like. There's a gain, a controller gain, and there's a zero and a pole. This adds the lead and this adds the lag. You can see it's a very simple type of controller, and it's got some advantages over a PID, but you'll see that in the end the PID does control a little bit better. We're going to use the same actuator, our plant type system. This is the motor gain, motor bandwidth. And this part would be the motor system, motor and load in velocity mode, and by adding an S in the denominator, we integrate the velocity into positions. So the method I'm going to use today is going to be different from the pole placement that I've used in the past. I'm going to use what I've heard called direct synthesis, and basically it's a way of brute forcing the kind of response that you want. And one of the things about this system is that we know that because there's two poles in the open loop transfer function, and the lag is going to add one pole, there's going to be three poles. There's going to be 1, 0. And what we're going to do is we're going to simplify the response by choosing a simple closed loop transfer function. So the first thing I'm going to do is I'm going to start out with the basic formula for a closed loop control. So we got the controller, the plant or actuator, and what we're going to do is we're going to solve for the controller. So we get this equation. So now, since we know the plant or the actuator from above, and all we have to do is specify the closed loop transfer function that we want. And what I'm going to do is solve for the controller. I'm going to substitute the plant transfer function, open loop transfer function. I'm going to substitute the closed loop transfer function that I want, and simplify and collect on S. And what I get is a transfer function. This is the controller transfer function. And it looks like this, and there's three parts to this. This is the 0, the lead part. Go back up here. S plus 2 times lambda is the pole, so we have the pole at 2 times lambda. And then the gain is lambda squared over the gain times the corner frequency or bandwidth. So just to verify this, I'm going to take these equations and substitute them into this equation to get this, and then simplify. And I get the characteristic equation here, the symbolic characteristic equation. And if I make some substitutions, remember I said that this is the 0. So I'm going to substitute alpha is equal to the 0. 2 times lambda is the pole, and lambda squared divided by the actuator gain times alpha is equal to the controller. I get a simplified closed loop transfer function, which has only two poles, two real poles. So basically what this method is doing is it's moving one of the closed loop poles on top of the 0, so they cancel each other out. So what we end up with is, instead of having a transfer function with 3 poles, we have a transfer function with only 2 poles. But that's at the expense, it removes one of the zeros. Then we can also check the transient response. This is very easy to do because we can do take the inverse Laplace transform as a function and convert it to time. And that's what I've done here. R is the step. I'm just assuming we're going to do a step change or a step disturbance. And then this is the desired closed loop transfer function. And this is the response as a function of time. So what you can see that is, as time goes to infinity, this is going to go towards 0. So we're going to be left with just the target position and times 1. The transient part is interesting in that all the terms are negative, and that's important. If all the terms are negative, then you know the system is not going to overshoot. If any of these terms are positive, it's possible that the response will overshoot. But it requires a 0 to get a positive response or an underdamped system where there's sines and cosines. So in this case, we know that the system will not overshoot no matter what. So to go further, I'm going to choose some parameters. I'm going to choose the same ones that I used for the PID. So I have my actuator gain of 10 millimeters per second per percent control output. So my maximum speed is 1,000 millimeters per second, or 1 meter per second. My corner frequency is at 10 hertz. If I invert that, I get the time constant, 16 milliseconds. And I'm going to place 2 poles at 2 times alpha, or actually they'll be at minus 2 times alpha. And remember, I'm only placing 2 poles because the 1 pole is going to be canceled out by the 0, as we saw above. Now I'm going to calculate the controller gains. So I have, this is the controller gain, and the controller pole, and the controller 0. You can see the values. And I'm also going to calculate the feed forwards. And this is fairly easy to do. I'm not using the feed forwards. Now here we get into some tricky part in the simulation. What we're going to have to do is convert from the controller from the S domain to the Z domain. And to do that, we're going to use a technique called matched Z transforms. And I like matched Z transforms because over Tustons, because it doesn't add extra zeros to the system, and it keeps the system simple, except for you have to do a little bit of scaling. So let's just go through the procedure here. What we want to do is we want to turn this controller into this controller, where this is the discrete gain. You know, this is still a controller gain, but it's the discrete version. And by doing this substitution, S plus alpha, this is alpha, is going to be equal to this term over here. And this is going to be equal to this term over here. So assuming that our time is, our update time is 1 millisecond, we can calculate the Z pole, in other words, the discrete pole, the discrete 0. And then we have to scale the continuous controller gain into the discrete controller gain so that the DC gain happens to be equal. So this really should be 1 minus Z pole times Z to the minus 1. But at infinity, you get the steady state when Z is equal to 1. So I just left the Z out. And after scaling, I get a gain of 91.715. The state space simulation is pretty much the same as the other versions, the other PID. There's this is the corner frequency. Basically, this is going to implement our open loop plant here in state space. And there's a 0 in here because we're integrating velocity into position. So this is the continuous version, and then to convert that to the discrete version, we have to do a Taylor's expansion, or it's actually would be called an EXPM equation or a function in MATLAB. Or you could use the C to D function. And that would convert the A and the B arrays over to the discrete form. So this is the discrete values. Now I'm going to implement the lead leg controller. And basically we have our initial state with position and velocity, initial control output, And then we have to have an error history, because what's going to happen is we need to know the current error and the error that we had previously. So what we pass to this is the target position and velocity. This is the actual position and velocity. This is the control output from the last time, and this is the error history. And the first step is to update the state using the current control output that was passed. We update the error history. So we have the target position minus the actual position. And then this is the lead lag filter implemented. You can see it's very simple. We have to take the last control output, multiply it by the z-pole value, and then we take the gain and we multiply it by the current error. This is almost like a proportional term here, minus z times the digital 0 times the error before. And this kind of implements the same thing as a derivative gain, kind of. Anyway, we limit that to plus or minus 100%, and we have the output. And notice we don't have an integrator, and because we don't have an integrator, we don't have to worry about winding up or unwinding the integrator. We're going to return the new state, the new control output, and the error history. And to test this thing out, I like to always use steps to begin with, because that tells me how the system's going to respond to step changes or disturbances, and I don't want it to overshoot. And you can see that it responds to steps quite nicely. What I find kind of interesting is that we expect the control output to saturate, because the error is 100 millimeters to begin with, and that's a pretty big error, and it's going to cause the output to saturate, and the system's going to accelerate to 1 meter per second, 1,000 millimeters per second, as you're going to see down here. What's interesting, though, is to look at the control output, and you can see that it's working hard. It's going, oh, let's go fast, 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 fast. Oh, we got to brake, then we got to go fast, and we got to brake. But still, the actual position goes right to the set point without overshooting, and that's just as predicted. And then when the target goes down to minus 200 or minus 100, you can see again it saturates, but there's an awful lot of accelerating and decelerating here. But again, it doesn't overshoot. And we can take a look at the velocities, and you can see the velocity goes up to, you see the velocity is on the right-hand scale here. We go to 1,000 millimeters per second, then it slows down, and what you notice here is that it doesn't go negative and then come back up. If it did that, then we would know that it had a position we had overshot. So one of the things that's nice about lead lag control is that you can make it so that it doesn't overshoot. And a lot of that is because there's no zero left to cause the overshoot, as what happens in a PID. But the downside is because you don't have a zero that extends bandwidth, it's a little bit slower than a PID. So let's take a look at how it does with a cosine ramp generator. This is something like what would happen with a real motion controller, moving from point A to point B. And in this case, we're moving 500 millimeters in 1 second, like in the other examples. And you can see there's a little bit of error between the target and actual position. But it's not great. If we use feed forwards, we could probably make this motion perfect. So this is actually pretty good. And now let's go down to the Bode plots. And this is the equations from above. Oops, going a little bit too fast. So this is the closed loop transfer function, as before it gets simplified by making substitutions for the controller gains. And you can see that because the result is only 2 real poles, the phase lag ends up dropping to only 180 degrees at the maximum. and the magnitude drops at the usual 40 dB per decade. Usually it's 20 dB per decade per pole when they're real. So this is exactly what we'd expect. Now the difference between this and the PID is that the PID would extend the gain out just a little bit farther. It would also have a little hump here because of where the gain exceeds 1, and that's due to the zeros. And the phase would be closer to 0 all the way out to about 4 hertz or so. So you get almost perfect tracking with the PID, but with the lead lag filter, you can see that there's a little bit of lag much earlier. And the motion profile that we had above, go back up here, was moving 500 millimeters in 1 second. But what's happening also is that we are ramping up in a third of a second, and then we're ramping down in a third of a second. So if you take a look at this, the frequency of acceleration up and down has a period of 2/3 of a second, or a frequency of about 1.5 hertz. So what we need to do is look at this point right here, and you can see that the magnitude is good, but we're going to have a little bit of phase delay. And that's exactly what we see. So the next thing I want to plot is or show is the graph the poles and zeros. These are the closed loop poles and zeros. And this pole is due to the open loop bandwidth. So this is the minus alpha. These are the two closed loop zeros up here. But you can see that our two closed loop poles here, there's 1 0 here. So basically what's happening is with this method, it's moved one of these poles from, normally I would have had 3 poles at minus 125, but this method has moved one of the poles to cover this 0, and therefore they kind of cancel out. So effectively what you end up with the response with these 2 real poles. And because all the terms are real but negative, we know that there's going to be no oscillations, which is what we have seen. And we have 2 poles, so that it's a little bit faster response than what you would have if you had 3 poles. And that's probably why we see the control output up here go positive and negative quite a bit with its hurry up and stop type of action. So let's just move back up here to show you what I'm talking about. Up, come on. Scrolling with the mouse takes time. This is a little bit harder control, or more aggressive control, and that's what you'd expect when you only have 2 poles as opposed to 3 real poles. So lead lag control works well for motors, and it's fairly simple to implement. The downside is you don't have a true integrator, so you might not get exactly into position if there's something to keep the actuator from getting into position. The other downside is that it's an all-digital type of implementation. So if this was quantized at this point right here, in other words, if the resolution is only, like, say, 20 microns or so, it would make it very difficult for this term to be smooth. So you would need to have very fine resolution to use lead lag control, as opposed to using a state space where you can use an observer to calculate or estimate the actual velocities and accelerations. So that sums this up.